So welcome everybody, and now we are going to start the lecture 4. So I think in the morning session you have seen we have talked about different kind of machine learning models like supervised, unsupervised and reinforcement learning. And in this one we are going to talk about the data collection and sensors and how the sensors being used to monitor the infrastructure and the data collection techniques, what challenges we could possibly face. Those are the important ones which we will see today. And then with that, first we will start looking into the different kind of sensors. There are definitely varieties of sensors, but we will look into the sensors which we generally use when we talk about monitoring the infrastructure. So here we will start with the most important sensor which is being used to monitor the infrastructure, and those are accelerometers. The sensors play a key role in measuring the vibration, shock and acceleration, so which are very crucial indicators of structural health. And what generally the accelerometer do? So an accelerometer, they measure an object's proper acceleration which is related to the free fall. For example, at rest on Earth, it measures about 9.8 meter per square. So these devices are widely used across the industry. They also been used quite a lot in consumer electronics, aerospace, scientific research, structural health monitoring. And the main applications, if you will try to look into this sensors, is one of the biggest one is the industry and consumer electronics. So accelerometers are used in aircrafts, they are being used in rockets, drones for navigation and stabilization, and in smartphones or cameras to detect the orientation and stabilize images. And then industrial machinery, so they are used to monitor vibration in motors, conveyors and any other kind of heavy equipment which are particularly valuable for early fault detection. And this also been used for ground movement and earthquake. So accelerometer detect the ground movement, which is vital for earthquake monitoring as well as structural safety. And if you will try to look into the emphasized used in the infrastructure monitoring for this accelerometer, you can see that accelerometers are commonly implemented for preventive maintenance in mining, oil and gas facilities, pipeline and offshore platforms and storage tanks. So they continuously measure vibration, acceleration to identify the deviation from normal behavior which signals possibly fatigue, crack or any other kind of structural issues. So by using this kind of sensors, or by deploying the accelerometer across the critical infrastructure, you can see that we can detect the problems very early, we can prevent the catastrophic failures, we can enhance safety, optimize the maintenance strategy. So they form the backbone of the real-time structural health monitoring system. Now if you will try to look into the different kind of accelerometer which is been available in the market or which we generally use for the infrastructure monitoring. So depending on their operating principles, the accelerometer can be tailored to specific application and environment. The first one is that machine piezoelectric resistive. So they are actually use piezoelectric materials to measure the vibration and acceleration. They are very common in industrial application. And the another one is the capacitive swing mass system. They also been used in MEMS device quite a lot. They measure the small acceleration with high sensitivity. Then the another one is the laser accelerometer. They employ the laser interferometry for extremely precise measurement when we are very much concerned about the small details of the measurement. And then the magnetic induction and optical accelerometer, they are also very useful in specialized environment where electrical noise must be minimized. Another type is the surface acoustic wave, which you also call as SAW. They measure the acceleration through the changes in the surface acoustic wave propagation. So when we talk about acoustic system, acoustic emigration, wave propagation, vibration, where we are interested about identifying the wave propagation, those are the places where we use this SAW. Then there are different other types of accelerometer as well, which includes strain gauge accelerometer, seat pad accelerometer, and LVDT based accelerometer. They all have their own uses and very niche uses. So one of the most common one is also the point out MEMS accelerometer. So most modern applications, especially if you think about the large scale monitoring system, we try to use the MEMS, which is the micro electromechanical system accelerometer. Because they are very small, so you can actually use them very often, and they are very low cost and can be deployed in the large numbers very easily. So you can also save some cost as well. So you can look into the behave under certain kind of load. That will help us or enable us to understand the accurate stress analysis. So you will see that especially for the big structures, there are a separate department. They kind of do the stress analysis. You will see the companies like Airbus or Rolls-Royce. There are separate department where their only job is to do the stress analysis, and they are being called as a stress analysis engineer. So you can understand the importance of stress strain. I think when we talk about the material, that's one of the biggest or important parameter we are always interested about to understand the proactive maintenance. So you can understand the value of this sensor is quite high, especially when we talk about infrastructure monitoring and how it's been actually used in experimental stress analysis. Okay. So now if you will try to look into that, there are three types of main strain gauges generally we use in the infrastructure monitoring, and this is we are talking about more into the as per the configuration look like. One is the quarter bridge strain gauge, another one is the half bridge strain gauge, and this one is the full bridge strain gauge. And these are actually based on how many active strain gauges are there, which is connected with the Wheatstone bridge circuit. Okay. So now if you will, so what is the Wheatstone bridge circuit? So basically this is the Wheatstone bridge is a electrical circuit used to measure the small changes in the resistance very precisely. So when strain gauges are attached to it, so this one, it changes the resistance due to the strain that can be converted into the voltage signal for accurate measurement. Okay. So now let's see one of these. So the first one, this is being called as a quarter bridge strain gauge. So only one active strain gauge is there, okay, for the first one. So there is only one active strain gauge is used with fixed resistor, 3 fixed resistor, okay. So 1, 2, 3. So there is only one strain gauge has been used here, and it's the very simplest and most common type of sensor we generally use. It's very good for basic strain measurement, but very less sensitive because we have only one strain gauge here. So now the next one is the half bridge strain gauge, and they use actually 2 active strain gauges here, and this increases the sensitivity definitely compared to the quarter bridge, okay, and also compensate for the temperature effect, so making it more accurate or practical application compared to the quarter one. And now comes to the last one, which is the full bridge strain gauge. So all the 4 arms of the Wheatstone bridge are active strain gauges here, and this configuration offers the highest sensitivity and the best temperature compensation, and this is very ideal for the structural health monitoring. So this is the very common type of strain sensor or strain gauges we generally use when we talk about structural health monitoring. And then now if you will try to choose between this configuration, they will depend on the accuracy required. That if you don't need too much accuracy, or if you need something in between, then you can use any one of this. But if you need a very precise model, especially when we talk about the safety or the bridges or the buildings, in most of the cases we use the full bridge strain gauge. So choosing on the between the configuration, that depends on the accuracy we need, the environmental conditions we have, the type of strain being measured, we actually kind of select it. So full bridge system, as I said, are typically used where very small deformation must be measured with very high precision. That's the time when we need it. When you don't need to kind of precisely measure that, then you can use this one as well. So the main takeaway from this kind of sensor is that understanding these configurations are very important, because that will help us to select the right setup for monitoring needs and balancing the cost and complexity and measurement precision. And then one of the very famous one, I think you will always go through that, that's the fiber optic sensor. So the fiber optic sensor, especially if you talk about the fiber Bragg rating, which is being called as an FBG sensor, which are becoming one of the very key technology in the infrastructure monitoring. They are also very important when we talk about preventive maintenance, particularly in mining and other high risk environment where we are talking about the human safety as well. So fiber optic sensors, they use the light traveling through the optic fibers to detect the changes in the strain, vibration, displacement and temperature. So how does it actually work? So FPG sensors are embedded or attached to the structure, and when the structure deforms, the reflected wavelength on the light changes, and this is how generally we measure the strain or any other parameters we are interested about. And what are the advantages of this kind of sensor? They are widely used in mining sites to monitor the health of the infrastructure. They can also measure strain, we can measure the vibration, angle, displacement simultaneously together. That's the best part compared to the other previous sensors. They also provide a full picture of structural health. So FPG strain and temperature sensor combined with interrogates can actually act as a complete data collection system for continuous and real-time monitoring. So it can, that's the way the FPG sensor are better compared to the other one, that it can simultaneously measure two things together. It can also combine with the interrogators and act as a complete data collection system. And if you think about the benefits, as I said, that FPG system monitor the effect of dynamic mining activity on structural stability by comparing strain variation over the time. So the data which you get from this, they can be transmitted to remote locations and recall anytime, and enabling a very proactive kind of maintenance and replace the reactive approaches. They also monitor the road pavement strain due to the mining subsidy, which is like a major risk. At an array of FPG sensors, they ensure that there should be an uninterrupted measurement, improving safety. So if you will try to look into this kind of FPG sensors, or the fiber optic sensors, you can, especially the FPG one. So fiber optic sensor, and here then we are talking about the fiber Bragg rating sensor. Okay. So FPG is one type of fiber optic sensor. So FPG, especially when we talk about, FPG offers a very high precision remote monitoring, and it also gives a real-time data acquisition. So this makes them very invaluable for predicting failures, ensure safety, as well as optimizing the maintenance schedule in mining and other infrastructure projects. Then you can see that what is the benefits of this kind of sensor. So by using the optical strain gauges, especially in the underground, we can monitor the infrastructure without exposing workers to the hazardous environment. So they don't need to physically go there. By using these sensors, we can actually monitor the health of the structure. This also boosts the efficiency of mining operations, reduce the cost and minimize the environmental risk. So if you now think about this sensor, we actually get the real-time data that allows to operate, predict, plan and optimize the maintenance activities instead of relying on the reactive approaches. So these are the main importance, the safety and efficiency are the main benefits of this kind of sensors. And if you try to look into the sensors, the main key features, you can see that fiber optic sensors, they provide very high sensitivity and very excellent accuracy when we try to measure the temperature, we try to measure the strain, displacement. They are very high sensitive. They are also very accurate. They are ideal for, as I said, large scale structures like tunnels, bridge, building, and they use a light signal passing through the optical fiber to detect even minute changes. So they are very precious over the long distance as well, which is critical for the early warning system. And their another advantage is the harsh environment. So they work well in the electrically noisy environment, or they are resistant to corrosion. So that's one of the very good benefit of this sensor compared to the other ones. And this makes them very suitable for high pressure or high temperature conditions where the traditional sensors may fail. If you think about PZT, if you think about any other kind of sensors. They also provide a continuous real-time data, which is very crucial for the structural health monitoring, or when we talk about very sustainable infrastructure. So basically, if you try to look into this fiber optic sensor, you can see that they are transferring the structural health monitoring by offering safer, more precise and real-time monitoring, and especially in difficult environments. This enables the predictive maintenance and improves the safety of critical infrastructure very well. So now you can clearly understand the advantages of this fiber optic sensor over the other one. Okay. And then definitely with this one there are different other kind of sensors like temperature sensors, humidity sensors, so which are also being used quite a lot. So the temperature sensor, which is very critical when we think about environmental monitoring, right, or structural condition where the infrastructure is, the environment is one of the biggest concern. So there are each type of sensors. If you think about the temperature sensor, one of the very famous one is the thermocouples. So these are made of two dissimilar metals that generates a voltage based on the temperature differences or changes of the temperature between their junction. So they cover a very wide range of temperature change and have very fast response time. So, but they are typically less accurate compared to other scenarios or other sensors. So if you want something very precise, definitely the thermocouple sensors are not good. But if you want something very quick, if you want that like a wide range of temperature, then definitely thermocouple sensors are one of the good one. But you may not get the accurate compared to the other sensor. Then another important type of temperature sensor, that is the resistance temperature detectors, which is also we call as an RTDS. So these are very fine where they often often made of platinum, whose electrical resistance changes predictably with the temperature. They provide very high accuracy and very good stability over a wide range of temperature. So making them very ideal for application, especially when you're talking about precise monitoring like data sensors or sensitive industrial process. And then thermocouple sensors, and then their resistance temperature detectors. Another important one of this kind of temperature sensor is that is the thermistors. Okay, so these are the semiconductor devices whose resistance changes very significantly with temperature. They are extremely highly sensitive and they respond very quickly. So if you compare the thermocouple with this one, so they do not have too much precision, whereas this one is having very good precision, right? But they kind of work in a very wide temperature, but they are very fast in response. Whereas for this one, they kind of they work in a wide temperature range, but they are not as fast as a thermocouple sensor. So if you need something very fast, if you need something very precise, then definitely we use the number 3. So they are kind of very significant with temperature, they are high sensitive, they respond very quickly. But the problem with this kind of sensors is that they usually operate over a very limited temperature range with, compared to the thermocouple or resistive temperature. So if you wind up looking for a very wide range of temperature, then definitely these two will be the best option. But if you're looking into a very minimal range of the temperature aspect, then definitely this one, because this one will not work for a wide range of temperature. Okay. So now if you will try to look into all of these kind of sensors, they actually, each type of this temperature sensor has its own strength, and thermocouple for wider range, as I said, and whereas the second one, RTD, is for precision and stability, and the third one is mainly for the high sensitivity. So the choice also depends on the specific monitoring you are interested, the needs of the infrastructure, the current, the temperature of the infrastructure, how quickly you want it, whether you want it for a wider range of temperature. So those are the important factors are needed when you select this temperature sensor. Then there is another interesting one which is the humidity sensor. So humidity sensor, which are very also essential for monitoring of the moisture levels in the environment. So when we are thinking about the environmental monitoring like data centers, tunnels, underground facilities where moisture level can be a tricky condition. So where controlling the humidity is very critical for the equipment performance as well as the structural integrity. So those are the places where we generally try to use this kind of humidity sensor. So definitely they do also have their own types and mainly you will see they have mainly 3 types of sensors for humidity sensor. And the first one is the capacitive humidity sensor. So these sensors actually measure the changes in the capacitance which can be caused by the water vapor absorption in a dielectric material. So these are being made with dielectric material. They are widely used because they are very accurate, they can be reliable, and again they cover a wide range of humidity. So they are perfect for monitoring relative humidity in a data center. And then the second one, or the second type of humidity sensor, is that the resistive humidity sensor. So these use a humidity sensitive polymer, or they are also made of some kind of metal oxide film, whose electrical resistance changes with humidity. So they are very cost effective solution for measuring the relative humidity. But the problem with this kind of sensor is that they have very lower long term stability and accuracy compared to the capacitive sensor. So if you want some stable, accurate one, definitely the capacitive humidity sensor is much better than the resistive humidity sensor. But if you kind of looking for something very cheap, cost effective for measuring this humidity, then definitely the second one will work better. Now if you will see the third one, which is the thermal conductivity or humidity sensor. So basically this measures how the thermal conductivity of air changes with humidity. So that's how it actually works. So basically if you will look into that, thermal conductivity of the air and how that changes with the humidity level, that's what this thermal conductivity humidity sensor measure. So they provide also very accurate measurement, very precise measurement over a wide range, and they making them very suitable for the environment where the high precision and stability are very, very important. So each of these sensors, you can see that for the humidity sensor, as again the same thing, that they have their own strength, they have their own weakness. Capacity for wide range and accuracy, whereas if you think about the second one, which is the resistive for cost effectiveness, definitely we are not thinking about quite accuracy for this one. But for the third one is that for high precision environment. So again, choosing the right type of sensor will ensure more reliable monitoring, better environmental control, cost effectiveness. Those are the all factors always been involved when you try to select the sensor. Then there is a very important and very interesting one which we call as an AE sensor, and that has been also called as an acoustic emission sensor. So what they do, they detect and convert stress waves from the material into the measurable electrical signal. So they are particularly very powerful for non-destructive. So if you work with NDTs and all, you must have used this kind of sensors, and they also kind of detect the early failure in the structure. So that's the reason these are quite famous. And how generally this AE sensor works? So AE sensor picks up an the elastic waves, which is entitled when the material is either stressed, they are being deformed, they are stuck somewhere, and these waves then occur well before the visible damage occurs. So you can actually early detect this, such as like cracks, fractures. So that actually making this AE and very early warning. So that's the reason it's quite different compared to the other sensor. Then the sensor convert the wave motion into the analog electrical signal, and which can be analyzed for trends and potential flaws. So what is the, if you try to look into this AE sensors, this AE method, because the way these AE sensors work is widely used to predict and prevent failures in materials and structures by identifying a very tiny deformation and minute cracks before the catastrophic failure. So even if there will be any tiny details of the changing of the deformation, stress, these are actually these AE sensors can actually catch that. As I said, that is a very common type of sensor which is being used in NDT, because it allows the continuous monitoring without damaging the structure. So that's another thing, that whenever you use this sensor, it's not going to kind of affect the structure. And now if you will try to look into the sensors, there are definitely varieties of these AE sensors. One of the important one is the resonance sensor. They are mainly commonly used for high sensitivity at specific frequencies. Then there is another type of AE sensor, which is the wideband sensor, and they capture a very broad range of frequency specimen for a full picture of AE events through the lower sensitivity. Then there is another one which is the high temperature sensor, and they actually designed for contact surfaces under very high heat when the temperature actually goes very high. And then there is another kind of AE sensor, which is the differential sensor. They are best when you have some noise in the environment. So when you talk about traffic or some kind of noisy environment, so differential AE sensors being used there quite a lot. And then there are a lot of other kind of AE sensors also, like miniature or some kind of specialized design for the specialized performances for unique kind of applications. So but you can see that compared to the other sensors, AE sensors are quite broadly used in a lot of infrastructure monitoring, because they are very essential for early crack detections and safety. And again, choosing the right sensor and the right sensor frequency. In practice, the AE sensor is selected based on their resonance frequency. For general, if you try to think about this acoustic emission sensors, they are, or the acoustic emission monitoring sensors with around 150 kilohertz resonance frequency generally are being used for this kind of sensors. Or for corrosion, leakage, and any other kind of acoustic emission signals also, this kind of sensors are used. But then the resonance frequency becomes quite low, so it goes to around 40 kilohertz, and that's quite common. So the choice of sensors actually, the choice actually ensures that the sensor is tuned to pick up the specific stress waves which is being produced by the structure, whether it's under some kind of changes. And now there is another important factor of this sensor, which is the bandwidth as well as the sensitivity. So bandwidth and sensitivity are also often some kind of trade-offs. So a wider bandwidth, they capture more frequency, but that will reduce the sensitivity. Whereas if you will go for a very narrow bandwidth for this kind of sensor, that will improve the sensitivity. but focuses on a very smaller frequency link. So broadband sensors are also ideal for spectral analysis and those things. For for application of this kind of things, try to select a very right kind of AE sensor and select the frequency, select their bandwidth, select the sensitivity. So these are the factors you need to take care of when you are trying to select the acoustic emission sensor. And as I said that they can actually kind of define the structural force, they can corrosion in critical infrastructure, sometimes little bit of fatigue as well, leaks. Those are the things actually, acoustic emission sensors are quite important. And now if you will try to look into the applications of different kind of sensors, you can see that how humidity and temperature sensors are applied into HVAC system to improve the energy efficiency, indoor comfort and sustainability. So now if you will try to understand each application area, the first one is definitely the monitor conditions. So these sensors are placed strategically throughout a building or throughout an infrastructure. Why? Because we want to continuously monitor the temperature and humidity in real life, right? So monitoring condition is one of the biggest important application. Then another good application can be understanding the air quality. So data from this sensor actually help us to measure the moisture content in the air, and this is very energy consumption, right? And another important one is that when you talk about this optimizing the energy use. So by constantly monitoring and adjusting the system indoor environment while supporting the sustainability goals. So that's also add-on. So integrating these sensors into the HVAC system, you can see that you can not only enhance the the comfort, but also plays a significant role in energy consumption as well as the environmental sustainability. And now if you will try to look into the other possible applications or other possible sensors, especially when you talk about how humidity and temperature sensors improve the building automation or indoor quality. Another important one is that building autonomous system. So by integrating this kind of humidity and temperature sensors into the building automation system, you can see that the facility can actually remotely monitor and automatically adjust the environmental control. So this is actually optimizes the energy uses, maintain as well as indoor quality. And then another important application of this kind of different sensors is that the indoor air quality management. As this is also some way similar, that by monitoring the humidity level, you can facilitate the managers that can identify, address the potential issues early. So basically those are the main the building automation system, indoor quality management and monitoring conditions. So these are the main HVAC system, building the automation system as well as the indoor quality. So these are the main type of applications we generally think about when we think about the humidity or temperature sensor. So this application show that how sensors go beyond just only the collecting data which we saw before, and they actively support healthier, more sustainable and more efficient building management. And then there is another kind of application. So especially when we talk about the AE sensor, so they play a very crucial role in data centric management and controlling the quality of the equipment. And how they do that? They kind of maintain the optimal temperature and humidity level, protects the sensitivity. So in data centers, what we try to see is that the controlling the humidity and the temperature is very critical to protect the electronic equipment, right? And excessive humidity can damage the server or storage system, leading to the operational control. So that actually maintaining this condition that helps to reduce the power usage effectiveness, which is also being called as a PUE for the data centers, which is a very key efficiency. And they are mainly applicable, or the previous one we are talking about the humidity and temperature sensor, where this one is more for the acoustic sensor. And then this acoustic sensors are also very good in quality control. So AE sensors are widely used in quality control to monitor the health of the magnetic discs or other kind of components. They can actually detect their irregularities such as like solder scraps or any kind of poor bonding laminations or any abnormal sounds in the motors or fans. So they kind of indicate the potential issues. So they can actually detect the poor welding in pipes as well. They can identify the leaks in the drums, monitor the rotatory machine to diagnose the faults very, very early. And there are several other kinds of different uses for these AE sensors. But what exactly we are trying to talk about the application of different sensors, that we know that these are actually helping us to monitor, or this is called kind of giving us the data, right, collecting the data. But except that, what are the other things this sensor can do? And that's the reason of understanding the application of different kind of sensor. So overall, if you will try to look into this particular case here, when we talk about AE sensors, you can see that not only the in that way or the industrial settings. And then if you try to kind of understand the diverse real life application of this different sensor, please remember that here we are trying to talk about any other applications of the sensor rather than just collecting the data. So we are trying to understand, except that, what are the other broader applications this sensor could possibly have. So these applications, if you will look into these all applications, they cover the safety critical, industrial and research settings. So the first one is definitely we are talking about highlighting the safety monitoring. Sensors can detect sounds that occur before landslides, on the formation of cracks in tunnels or underground spaces. So this early warning actually help us, or they have the capability for to understand the disaster prevention and public safety. And another one is the industrial or research testing. So they are using tensile testing or kind of fracture toughness testing to understand the material behavior of under stress. They also help in detecting some kind of superconductivity, which is very essential to maintain the stability of superconducting system. They also kind of in power transformations or transformers, or this kind of sensors can detect some kind of discharges, and which is very critical indicator when we talk about insulation breakthrough. They also monitor the crack in pressure vessel, as I said, some breach piers, some rolling mill stand, which helping to prevent the catastrophic failure. So additionally, they detect the leaks in the pipes, as I said, storage tanks, which is very essential for environmental protection and cost saving. So these applications actually demonstrate, as I said, that how sensors can act as an early warning. They can also act as a quality assurance system across the multiple industries, from infrastructure safety to the data center, that means the high-tech research. That actually involves or improve the both reliability and safety of the infrastructure, and some way the mankind as well. Now we are talking a lot about the applications of this sensor and how how useful these sensors are. But we also have to remember that when we talk about the applications, there are a lot of disadvantages and limitations for all of these sensors, and we are always very much concerned about understanding the limitations of each of the sensor before selecting that, right? So the first one is the accelerometer. So accelerometer can be very highly sensitive to the environmental noise or vibration that are not the part of structural response. That can give you or some kind of false data, right? And which may affect the quality of the data. And then they also require very proper installation and calibration. And if you do not do it correctly, then there can be some bias and errors that can trick you, right? And they are also very power consumption, may limit their use in the long term or the remote deployments where battery charges are very difficult. So that's also one of the key limitations of the accelerometer. They also have very limited sensitivity to very low frequency. When you need to kind of take care of the low frequency event, they have very limited sensitivity, especially when we talk about large scale structure. And that can maybe cause them to miss some critical slow changes which can possibly occur, right? So they are the main limitations of the accelerometer, which is one of the commonly used sensor in the infrastructure. And then there is another commonly used sensor in the infrastructure, which is the strain gauges. And how they are being used? Strain gauges have very limited measurement range and can fail under large deformation. So when we talk about small deformation, then definitely the sensor strain gauge is quite good. But when we talk about real life structure, when we talk about the large deformation cases, they actually do not work good. Okay. And then another one or another limitation depends on the additive bonding you use and the installation quality. That means the quality of the installation, the bonding you are using, that's very important. If you use some poor bonding, that can lead to inaccurate readings, right? And they are also prone to drift over time. So you need to always, over a period of time, you have to recalibrate the sensor. And then also this kind of sensor is susceptible to temperature variation unless you properly compensate, which can distort the measurement. So these are the main limitations, but you also have to kind of look into the advantages of this sensor. So these limitations don't mean that the sensors are unreliable, okay? They just require careful selection. When you select your problem, that how you gonna monitor it and what are the key factors you need to consider during the monitoration, then you need to careful selection, you need calibration, you need the maintenance to ensure that accurate and meaningful data in the real life application is being done. But you have to also remember that these are always, for all of these sensors, there will be some kind of disadvantages or the limitation will be coming. Then we will look into the other two types of sensors. One is the humidity sensor and one is the AE sensor. So if you will see the humidity sensors, they are very sensitive to the contamination, they are condensation or dust, which can degrade their performance. And then they may also have very limited long-term stability, and therefore often they require frequent calibration. Compared to the strain gauge, actually they need more frequent calibration. And they are narrow operating temperature range. So the temperature range is most of the cases are very limited, and that can actually limit their use when we talk about extreme environment. When we talk about where the temperature can change vastly, right? That is very hot or very cold conditions. Those cases the humidity sensors may not perform quite well, right? And then as I said, another important one, which is AE sensors or acoustic emission sensors. So they actually generate very large data in volume. That means that most of the cases you need to use some kind of machine learning algorithm. Otherwise, your analysis become very complex, and you require some additional advanced software to kind of monitor that. So when you have this data, you cannot itself generate that. You need some additional data, or you need some additional kind of software to analyze those particular data results. And they are very sensitive to the background noise and environmental interface. That means which is not coming through the structure as well, and that can actually may mask or distort the signals of interest, which is not coming from the infrastructure we are interested about. And again, they have a very limited effective range, so multiple sensors may needed to cover the large structure. So the number of sensors for the acoustic or AE sensors are always much more, because their range is very small. And again, their installation, their maintaining costs are much more compared to the other one. They can be really relatively high compared to the simple sensor system. So and also the person who needs to install and maintain that, they need to be well trained as well compared to the other sensors. So it also needs a lot of human training to install this kind of sensor. As I said, that this limitation highlights the importance, not only what you don't need to do, but this is also actually educating us that the importance of careful planning, the importance of the placement and the maintenance when using this kind of sensors in the infrastructure monitoring. So by understanding these challenges, we can design better systems and improve the reliability, right? And then definitely there are two other types of sensors, which is the fiber optic sensor, temperature sensor, right? And FBG, as I said, are they are one of the very important type of sensors in the infrastructure monitoring, but they do also have their own limitations, and we need to be careful about selecting those kind of sensors. So fiber optic sensors, they often have a very high initial installation cost, which can be very barrier when we talk about the large scale projects, right? And then they require specialized equipment for installation, for interactive, and also interpreting the data. So once you have the data, you also need a specialized software to kind of understand that. And the fragility of the optical fiber in harsh environment or physically demanding environment can lead to damage or failure. And there are also very signal attenuations over the long distance, so which can reduce the accuracy, and they require signal boosters sometimes or repeaters, right? So that's the main kind of limitations of this optical or the fiber optic sensors. And then comes the last one, which is the temperature sensor. The temperature sensors actually, they typically provide point or limited area measurement unless they are network, or they may miss the spatial variation, right? That means you need more number of sensors for the temperature sensor. They also require robust protection to survive the outdoor harsh environment. Their accuracy can influence by the sensor placement or external heat sources, which may not be related to the structure itself. So it can actually get affected from the outside as well. There will be some kind of external heat, not from the infrastructure but from outside. So as I said, that these limitations actually show the cost, installation complexity and the environmental condition must be carefully studied, must be carefully considered when we are trying to select this sensor or kind of deploying this sensor onto the structure. And when we try to understand this, so by addressing these challenges very early, we can ensure that we get the reliable data and we get a better decision making, right? So they are the main limitations of the sensors which we generally talk about. And then comes one of the very important factors, which is the automated data acquisition system, and we call it as an ADAS. And that is nothing but the electronic device which is being designed to automatically read, store and transmit data from various sensors, which is used in mainly geotechnical, environment, structural monitoring, right? And what is the purpose and the scope of this ADAS system? So the ADAS actually plays a very key role in monitoring dams. They also have very other critical kind of infrastructure. They are being used a lot because the systems are often deployed outdoor when we talk about the harsh environment. When you have a temperature on a very high or low temperature, they must be robust, they must be modular and capable of handling a spread out of the data sensor network, okay? And then there can be two types of monitoring which could be done using the IDAs. One can be static, one can be dynamic. So this presentation or this slide, if you will look into that, we are trying to talk about ADS, or in the particular lecture we talk about ADS into more static measurement. We are not talking about much dynamic, but if you talk about the static one, for example monitoring a long-term structural changes, right? But if you talk about the dynamic one, then acceleration due to the earthquake, right? So that's how the generally this ADS system work. It can work on the static one, we can also work on the dynamic one, but for most of this part of this lecture you will see, we will try to talk about the static part, or the problems we will be talking about more the static measurement. We will also do a little bit of the dynamic measurement as well. And the advantages or the key feature of this ADS system is also they are very low in power consumption. They are very robust when you think about the long period of time in a very remote location. The modularity and the ease of the deployment is very easy. So that is make it possible to scale systems very easily. And they have a very diverse network configuration, and they are very good in so that actually helps you to get the seamless data transmission very easily. And another important or the key features of this ADS system is that this feature ensures successful field deployment and reliable data acquisition. So again, what is this ADS is? We call it as a automated data acquisition system, and they are actually electronic device. They are designed to automatically read the data, store the data, transmit the data from various sensors used in any kind of structural monitoring system, right? It can use environmental monitoring also, it can use any kind of other structural monitoring also. So now if you will try to look into the modern developments which are happening with ADS, because ADS is still ongoing research area, there are a lot of researchers still working on this. You can see that how modern ADS solution actually support the real-time monitoring. So they are also kind of trying to work on the low cost. If you will see, there are many labs where the researchers are trying to develop a very low cost ADS system, or low power radios, even elimination of extensive surface cabling, which can make the very easy to carry as well, and very easy to put into a remote place as well. So this can actually kind of help you to cut the cost, improve the system flexibility and all. So basically these ADS systems are at the heart of the modern infrastructure monitoring, and they actually kind of if they design properly, they will help you to or enable you to the continuous monitoring, the reliable monitoring and efficient data collection even in the remote or the challenging environment. So now if you will try to deal with the big data, or if you try to deal with the large volumes of data, you can see that the data set is considered as a large volume when it exceeds the capacity of the computer's main memory. That's one we call this as a big data, right? So that means it cannot be processed all at once, and they require a specialized approach. That's the time when we call that we have a big data. So these data sets are massive, right, and they ranging from hundreds of gigabytes to the terabytes or even petabytes, right? And this sheer scale makes the traditional process methods very difficult. So they often also involve the diverse data types like structured data, semi-structured data, unstructured data, so which complicate the analysis and the storage also very complicated. And then data can be generated and arrives at a very different speed, right, at a very high speed, often in real time or maybe not in real time, right? So this demands a very fast processing and the immediate decision making, especially because we are talking about real time monitoring here, right? So if you talk about this big data includes not just the text, but also it can include images, right? It can include videos, it can include some kind of sensor reading, it can include some kind of social media feeds and many more. So it's not like only one type, they can have varieties of this kind of big scale data. And the diversity calls for very advanced tools to integrate and analyze the information. So sometimes we will see that you may get a mixing of that as well. So big data is not just about the size, that means it may be, it may be on hundreds of terabytes or even petabytes, but it also depends on the type of data you are getting. It's also about the speed you are getting, the complexity and the diversity you are getting. So understanding these characteristics that also will be very important and help us to design better data acquisition. They also help us to design the storage and the analysis system very well. Now if you will try to look into the challenges of this kind of large data sets, there are varieties of the large data sets challenge which we see. And while big data offers a huge opportunities to understand the structural behavior in a broader way, it also induces a technical and operational difficulty that needs to be carefully managed. So one of the important one is the storage. Definitely that we all kind of struggle with. So the large data sets, they require substantial storage capacity. This can be expensive and difficult to manage, especially when maintaining the infrastructure for multiple users, right? and efficient tools that avoid unnecessary data duplication. That is also very, very important. And another important challenge which we kind of deal with when we talk about this big data is the access of those data. So collecting and integrating large data set can be resource intensive, right, and time consuming. So ensuring the data quality and the consistency during the transfer between the system or across the network is also very, very challenging. So compression and efficient transfer protocols are critical to address this issues as well. And then the tools, that's the one the traditional plotting and analysis tools often is not suitable for big data, right? We cannot use the normal one. So there are some kind of specialized and scalable tools which needs to be there, and that needs to be visualized and extract as a combination of hardware optimization as well as advanced software techniques. So without the software technique and the hardware, just with some kind of traditional or manual plotting tool, we cannot analyze this data. And the last another important one is the resources, right? So the processing and analyzing the large data sets, they demand a significant computational power. I think that's something very, very important, that running the computation we need some HPC. Definitely impractical to do that. So distributed computing framework like Spark, or there are hand loops, they are used parallelly or distribute the tasks together. So or sometimes HPC, that's also another resource. So you need resources to kind of take care of the big data. Just using one laptop or one computer itself or one computing system will not help you to analyze the data. And they are the main type of four challenges you can see, which is storage, access, tool and resources. And they highlight why big data needs advanced infrastructure and careful planning, right? So overcoming these challenges is very, very essential to unlock the full potential of the large data. And then if you try to think about the strategy, so when we try to talk about storage of the large data sets, so there are several strategies we kind of use it. One of the very important one is that distributed file system. So basically what we do is that we try to the systems like head of distributed file system, which is also been famously called as HDFS. If you work with the machine learning or big data sets, you must have heard about it. And then there are cloud-based storage distribution, like we use Dropbox, G Drive. There are so many ways to do that. We use it to store the distributed data across the multiple nodes. And this parallel storage approach makes the handling large data sets very, very efficient, very, very scalable. And then another way we do is that columnar storage, right? So then we using a columnar, what we do for this kind of cases here, that this breaks the data set into very small and manageable sections or the small and manageable subsets or groups. And that what does it do? The small and manageable subsets or groups. And that what does it do? It actually helps the query speed. It actually helps the performance, especially when we talked about the time span or categorical data. We take care of that. So compression allows space, right, and without sacrificing the data quality. And however, it's essential to balance the compression and query performance to avoid the slowdowns. And then if you will see that each of this kind of organization choice or the storage strategy, they will actually depend on its need and infrastructure. That how choice or the storage strategy, they will actually depend on its need and infrastructure. That how we kind of want to take care of that. And understanding the pros and cons, definitely they do also have their pros and cons of those very clearly. And that can help actually as an engineer for us to optimize how they can be stored, how they can be analyzed later and access the large. And there are different ways we do that. I think all of you must have heard about sampling techniques. We do also use sampling. Often you don't need to use the full data set. So you can see that there are a lot of sampling techniques, the Latin hypercube, or there are Sobol sampling techniques. So what we do is that we don't need to use the 10,000 data. Among those 10,000 data, we may select 23 or 50 data sets which we may need to use it for our case. That's been actually called as a sampling technique. So sampling a subset of data can speed up the development, right? They reduce the computational cost, and they are being used quite a lot when we talk about machine learning approaches. However, it is very, very important to note that this may introduce some kind of bias or maybe miss some data patterns. So that's very, very important that you do your convergence study, you do your Monte Carlo simulation, and you see that how exactly your data looks like with 10,000 samples. And then with the sampling technique, different kind of sampling techniques, with the different ranges of samples, to match which one is giving you the exact result. So the convergence is very, very important during this one. And then another important one is the parallel much efficiently. And another important or another very useful one is the feature engineering. So they are basically creating a meaningful variable from the raw data. that makes like machine learning model, we use this quite a lot, and in the machine learning model they become quite effective when you try to use this feature engineering. This could actually include dimension reduction, grouping or normalizing. So basically clustering, grouping, those kind of things actually come under the feature engineering. So basically you are grouping the data so that you now understand, okay, among this big data this looks somewhere similar, and then you analyze this data further, right? And then data quality check. That's very important when you talk about the large scale data. So data quality checks and validation rules, they ensure the accuracy, they ensure the consistency of the data, or you need to understand whether there is some noise. So if you will see, most of the cases we also do some kind of noise study to understand whether there is some noise in the data. So interestingly, AI and automation tools are being used to streamline the process and maintain a very high data integrity. So these steps are always together ensures the data you are working on, they are clean, they are noise free, they are reliable, they are ready for analysis, which is especially important when you talk about the data projects, right? And you can always see that most of the cases definitely we use it somewhere together. So it does not also necessarily mean that there is only one of these processes you will do. It can possibly happen that you may use one or two of this in your data calculation, right? Now if you will try to visualize the data and explore the data, so large data set can be very overwhelming, right? Visualizing is very critical for understanding the data and spotting the trends and deriving the insights of this data. So as I said, that sampling is very important, that instead of trying to visualize the entire data set at once, we can take a random sample. So sampling techniques can be very different, but you can take random sampling, you can take some deterministic one, that depends on how you actually choose it. This makes it very easier to get an overview without overloading the visualization tools, okay? And then there is another important one, which is that aggregating the data before visualizing. That will help to reduce the number of data points which is being displayed. That will make the process much faster. That will improve the clarity and improve the performance, okay? And then definitely the interactive tools. So interactive tools, or you will see there are a lot of visualization software, there are a lot of visualization tools are nowadays being used that let the users or the engineers export the data dynamically. So there are a lot of softwares are now being used quite a lot. So they allow you to drill down into some subsets of the data. They're making it easier to uncover the hidden patterns as well as the relationship. And it's been quite used a lot when we talk about unsupervised learning. You see that people use these things quite a lot. And again, if you will try to look into the industry approach or how the industry kind of work with this large data sets, you can see that nearly every industry today use large data sets, from finance to the telecommunication, healthcare, and agriculture, education, infrastructure monitoring, government. So each is learning how to harness the growing scale of data, right? So handling the large data sets effectively is a key to innovation. So organizing how to kind of analyze that, how to manage and visualize their data, that can actually unlock the insight that improve the decision making, that will also improve the productivity and the competitiveness of the market, right? So in summary, if you will try to look into this particular visualization methods, you can see that the data visualization as well as data exploration, they not only make the large data sets very manageable, but also open up opportunities for the organization or the companies or the industries to innovate and drive better outcomes. The more data you have, the more range of information you have, and then you can analyze the whole thing in a better way. And then, as I said, that the importance of the data processing, which is the foundational phase of the any data analysis or machine learning pipeline. So it is about transforming the raw data into the structured data, into the clean, critical for us, not too much complicated to understand, but the information we need to know that how this big data can be, So I hope you will not have too many doubts compared to the other one, but we will try to take the problems or the questions after this. So then, as I said, that the data processing has become very essential when we talk about the big data. And you say that we are talking about the big data, we are interested about the big data, because we are talking about the sustainable infrastructure monitoring using the AI. So definitely, big data is something we are absolutely interested about, how to gather the data, how to store the data, process the data, analyze the data, and the more important thing is that get the right amount of data or the clean data, right? So today, if you see the data flows in form of IoT sensors, social media, or even the cloud apps or the any kind of other legacy system, you can see that all have some different kind of formats. That the quality standards can also vary. So pre-processing ensures that this raw data is clean, as I said, they standardized, they made usable for analytical or analytics and AI models, right? Because we cannot actually process this without using the AI model. So there has to be some kind of link to this data. So poor data quality can actually cascade through the entire analytical flow. Without proper pre-processing, models may actually become really biased, miss the important patterns, or fail to generalize to real world scenarios. So this is especially dangerous in industries like healthcare, finance, where bad data can actually lead to the discriminatory decision or the compliance issues. Okay. So basically the key takeaway to kind of data processing and why it is critical for the modern society is that data processing is not optional. Which is a foundation of preparing data for analysis and machine learning. So there are certain steps which ensure the data quality, the consistency and usability. So in the center you can see that we have a data processing, and around that there is format, scaling those, encoding those to make it suitable for analysis. And then comes the data reduction. So the data reduction is reducing the data volume or dimension. And modern data processing goes beyond this foundation steps to include automation, feature engineering, real-time quality check, real-time quality check. So these are the, it needs to have clear data, cleaner data, more integrated data, and more manageable data, which directly improves the quality, also speed of the downstream analytics and the machine learning approach, right? And now on this, you can see that the integrating the data, that how we can integrate this data. This is about combine the information for multiple heterogeneous sources into the unified flow. And this is very crucial for reliability analysis or the machine learning approach. So data integration has actually evolved beyond the simple concentration, and modern approaches, they preserve the semantic relationship across the different data types. They resolve the schema conflicts, they maintain the data lineage. So we are actually talking about combining the operational system, external APIs, as well as the historical archives into one cohesive real-time system. Okay, we are combining all of this together. And here you can see that we always can try to identify and merge records which referring to the same entity across the different data sets. And this uses advanced matching algorithm like string similarity and those things. Then data fusion, I think data fusion is one of the very important process. And this is the process of integrating the information from multiple sources, and then it applies to the conflict resolution. It's been used quite a lot in uncertainty quantification, semantic reconciliation to create a very comprehensive authorized data. And then if you think about the modern trend, the modern integration workflows are cloud native or very much cloud based, and they support both batch and real-time scaling, right? So this hybrid approach, they minimize the and they support the time-sensitive analysis. They allow the continuous data flows from the system. So if you will try to kind of look into this data integration, you can see that this is actually lays the foundation of trustworthy large-scale analytics by merging the disparate data sources while preserving the meaning. And definitely we are concerned about the quality, we are concerned about the meaning of the data you are getting, we are also concerned about the timeliness of the data we are getting. And another important or the key steps in the data processing is the data transformation. This is about intelligently cleaning and reshaping the data so it optimizes for the analysis as well as the modeling. Okay. And how do we do that? So data transformation today is much more than simply just normalizing or scaling, right? It now involves intelligent automation. It also kind of context aware of processing, right? Which can adapt to the data's characteristics that needs of downstream model. So modern workflow, they use machine learning models to guide the pre-processing decision so that the transformation actually enhance the predictive code rather than degrade it. And the development you can see throughout this for the data processing method or the data transformation is that we are seeing deep learning models are used quite a lot for sophisticated input or imputation of the missing values, right? And then also assemble the methods which are being applied for outlier detection. We also kind of see the automated quality assessment tools are being used continuously to monitor how effective the transformation can be. And all these approaches outperform traditional route-based cleaning definitely, especially with the complex data sets containing subtle of the quality issues, right? So then there are a lot of like advanced cleaning areas which are being used, something like intelligent outlier detection or context-aware missing value imputation, automated duplicate removal. So these are the type of advanced cleaning areas or cleaning tools we use. So automated duplicate removal is one of the important one. So why we do that? So this is mainly used for the non-probabilistic cases. This uses fuzzy matching and record clustering to identify the near duplicate that traditional hash-based approaches cannot do that or sometimes miss it. or improve the data consistency. So basically what they do is that they try to match and record the clustering, and they identify the very near duplicate one, may not be the duplicate one, but very near duplicate one. That's actually been quite used a lot when you think about the fuzzy, where you are having some kind of triangle and you don't know your distributions. You are trying to get all the distributions. You need to be very aware of the data you are getting and the duplicates so that you can avoid it. So we will try to kind of understand all of this together. You can see that modern data transformation, they turn very raw, inconsistent data into a very high quality input for analytics and machine learning. So by using very intelligent, automated and context aware methods, we actually can achieve a better model performance and more reliable insight. And then comes the another important factor. So continuing with the data transformation, we can see that how modern techniques actually extend the foundation we have already covered. So these methods aim to actually make pre-processing more intelligent, more better aligned with the structure of the data. So one of the important one is that adaptive feature scaling. So instead of applying a single scaling method across the entire data sets, what we could do for this kind of case here is that adaptive feature scaling, they tailor the normalization strategies to each of to feature the subset, okay? And this preserves the important signals in the data while ensuring that the compatibility with the algorithm we plan to use. So that's the adaptive feature scaling. Whereas for the semantic categorical encoding, what we do, we have the traditional encoding methods like one hot can be arbitrary. So what this kind of encoding does is that they kind of encode instead of leverages the relationship. That means they kind of try to use some kind of categorical data. And another important one, last one, is the distribution aware discretization. So this approach is rather than fixing the binding, what this approach does is that they kind of automatically determines the optimal bins for continuous variables using the entropy minimization based approach. And this leads to more informative, that means you get more information and less biased features representation. So basically all of this kind of data transformation, these are all modern data transformation. They are not the previous methods. They are very modern transformation technique. They go beyond one size fits all pre-processing, okay? And they adapt to data's underlying structure. They kind of preserve the meaningful patterns and they improve the model performance downstream. And then another important factor is that the data reduction, that is also a very crucial part. We need to understand which data is important and which are not important. So especially when the data set grows larger, it becomes very vital to reduce their size while keeping their protective power, right, or predictive power. So modern techniques go beyond traditional systems or traditional dimension reduction. There are traditional dimension reduction methods, but then there are separate, the modern ones like intelligent dimensionality reduction or automated feature selection or adaptive sampling. So what they generally do or why it is important? So data reduction improves the storage efficiency, definitely. They reduce the computational cost, they enhance the model performance. The goal is not just to shrink the data, but to optimize the features so that the models can run faster. But it not only will run faster, it will also give you predict the results better. That's very important. And for that we use, generally there are three key methods we generally do that. One is the intelligent dimensionality reduction. So this method actually combines the traditional techniques like PCA with more advanced tools like autoencoders, which we are seeing today, and sometimes some manifold learning. So it actually captures the nonlinear relationships in the data, and then while reducing the feature space, this is also especially powerful for complex data sets. And then there is another one which I said, which is automated feature selection and adaptive sampling. So what is adaptive sampling? This approach actually strategically samples the data. They use the stratified or importance based sampling, and this is also one kind of sampling method we do use. So we keep the most representative data points while reducing the data size. So using the sampling technique, that can be random, that can be selective depending on what you are doing. Most of the cases we do random samplings. And that actually is especially valuable when working with very, very large data sets. You have maybe 20,000, 20 lakh data sets, but among those you kind of try to understand using the sampling which data set you actually gonna do, and it actually becomes very less expensive. So the key takeaway, if you will try to look into that from this modern data reduction compared to the the conventional one, is that they integrate the feature selection. They also kind of use the model training intuitively. And this ensures that our reduction choices improve the final model performance. We are not only concerned about the computational cost or reducing the the data set, but we also need to be very much careful about the performance or the final model performance we are selecting, rather than just reducing the size, the sake of it. So that the performance is something very, very important when we talk about reducing the data. And then when we talk about the importance of data processing, so pre-processing data is very, very important. Pre-processing is also another very foundation for reliable one, and the key idea is that we explain the shift, right? We emphasize what needed today. We also wrap up with what is the important part. So if you will kind of look into this, that's what I have tried to highlight into that we have moved from basic cleaning operations to the intelligent one compared to the previous one. We now kind of use automated systems because of increasing the complexity of the data or the modern environment, and we try to understand the importance of the data-driven decision. So success today means embracing both foundation principle as well as the emerging technology. So if you will try to look into this pre-processing methods, you can see that the key takeaway is that effective data pre-processing that should help us as an, if you think about the industry, if you think about being a structural engineer, to transform the raw unstructured data into the trusted actionable insights, then that is very, very essential for any robust machine learning or analytical pipeline. And then we talk about the data processing methods where we're talking about data cleaning. As I said, that's also very, very important, the how you are handling the missing value, right? And there are several steps how we do that. First one is definitely identifying the missing value. So use the descriptive statistics, or there are some visualization methods to find the columns or features for missing value, and this often appears as NaN or null in dataset. And then assess the impact, that what is the impact of this missing value, how missing data can impact your analysis or model, and look into the percentage of the missing data per column, or how important the column can be for your overall performance. And then remove the rows of the columns if they are small. So if only a very small percent of data is missing or is not critical for your performance, you can actually remove those rows and columns. And definitely the another one is that input the values when needed. So for numerical data, you can actually input the missing values with mean, median, there are more which we use like in that way. So for categorical features, you can actually input using the most frequent category. So basically you have to understand what data is missing, how impactful that data is for your analysis. Whether it's a very small data, small subset, then you can definitely ignore that. But if it's a very, very important one, then you need to kind of add that or input that, okay? So in short, basically handling missing values, they are effective in the first step towards building reliable machine learning model. So once our data is clean, we can actually confidently move on to the further pre-processing steps, okay? So now, because we have seen a lot, we have kind of gone through a lot of details. So now let's see one or two quizzes here. So when which of the following best describe the main purpose of data processing? It only reduces the size of the data set, or it ensures the quality and trustworthiness of the downstream insight, or it replaces the traditional analytics entirely, or it only involves the cleaning missing data. So when you talk about the data pre-process, does it only reduce the size of the data? No. Does it ensure the quality and trustworthiness of the downstream insight? They do, right? Does it replace the traditional analytics entirely? No, right? We add on stuff there. And does it only involve the cleaning missing data? No, that B is the correct option then, right? Clear? B? So now let's look into this one. So modern data processing, they combine the traditional methods with automated quality monitoring, synthetic data generation and real-time adaptation. Is it true or false? True? Right? So now again we will get back into the handling the data processing methods. So you can see that handling the outliers is also one of the important factors. Outliers are data points that differ significantly from rest of the data. And there are detecting and treating the outliers, they are very, very essential to ensure that the models learn from the patterns, the model learn from the exact pattern of the infrastructure rather than just the noise, okay. So if you look into the points which I have tried to highlight here, they outline the practical steps to identify and handle the outliers. First is that visualize the plot, okay. So start by using the box plot and histograms we use the scatter plot, and visual inspection often gives us a very quick understanding or quick sense of what the outliers are, right? And then we use the statistical measures like calculate the key summary statistics, like we use mean, standard deviation, interquartile range. So those are the kind of outliers actually kind of help you to typically define or understand that. And then remove the outliers when appropriate, right? If outliers are due to data, entire errors or anomalies, then you can remove them, use the filtering technique based on statistical result, and you can do that systematically, right? And then apply the transformations. So basically transformations such as log, square root, box, those are the normalized data, and we can reduce the impact of the outliers without removing the data points. We can do that. So basically, and then there is also when the outliers are unavoidable, you cannot remove that, or you cannot kind of remove those data. So what we try to, or avoid the data. So what we generally do is that consider the model that are less sensitive to them, like so SVM, like support vector machines, they are, or the random forest or the assemble method. This can handle the irregularities more well. If there are some kind of irregularities or noise, you think you cannot remove that, or that's very unavoidable, then you use some kind of AI models which can actually take care of those. There will be some kind of irregularity, but this kind of models can take care of that instead of using some kind of other traditional or like ANN or other things, right? So choosing the AI models can also be important in that period if you have some noises, if you have some irregularity in your data and you cannot avoid that. So basically handling the outliers is about balancing the data integrity and model performance. So by visualizing, analyzing and transforming, or using the robust model, we can ensure the outliers don't distort our insights or predictions. And then when we are looking into handling the duplicates, that's also another important part of data cleaning. So duplicate records can actually skew the analysis or the model the training because they inflect certain patterns or biases in the data set. So identifying and removing the duplicate, they are very important because they will ensure every data point contributes equally. They improve the quality, reliability of your machine learning model. And how generally we do that? First we identify the duplicate. That means we use the functions to identify the duplicate rows based on the specific columns or across the entire data set, and then we remove that. So remove the redundant records. That means if duplicates add no additional information, you can remove them with methods like, there are a lot of methods we can use to similar functions or tools. And then there can be some special cases, like sometimes duplicate because of the multiple entities, you still have some unique identifiers or subtle difference. In such cases, what you do is that you ensure that you retain the unique identifier or key columns to different between the records, right? So basically by following these steps, you can ensure that your data set is clean, free of redundancy or reliable for analyzing or the modeling. And this helps to prevent the skewed pattern and improve the accuracy of your prediction. And another important part is the data normalization, so which is the key data processing technique, and this is being used quite a lot to scale and standardize the feature value within the data set. So the main goal of this kind of data normalization is to bring all features into a comparable range without distorting the relationship between the data sets, right? And so normalization is very important, as I said, because many of the machine learning algorithms, especially those with the gradient descent, they perform better and coverage faster when the input features are on a similar scale or distribution, so the distribution has to be some way similar. So without normalizing, the features with large numerical ranges can be dominated in the learning process. So especially when you talk about stochastic or random samplings or those kind of cases. So the benefits of this is that definitely prevents the dominance of large scale features. That means it helps to prevent the features with large scale from overpowering those with the smaller scales during the model training. It also speeds up your training. That means your algorithms, when you use the machine learning algorithms like gradient descent coverage more quickly when features are being normalized, which means that the shorter training period is required, your time period actually reduces, and it also improves some way your performance, right? So normalization also reduces the impact of the outliers. It also kind of improves the comparability or the convergence period, okay? So in short, you can see that the normalization is very important because it creates a level of playing field for all the features, leading to more stable data. You can get more efficient data and more accurate model training, but it also some way helps your Though we are using the machine learning models here, we are still kind of concerned somewhere the computational cost. So this also kind of helps you in the computational cost. So there are different ways we can do that. So if you will look into this too, so what is the first one is the min max scaling, and the second one is the Z-score normalization, which is the standardization also we can see. So basically min max scaling is nothing but it's scaling which rescales your data to fixed range, usually we have a quick look into that. So basically it uses a formula that talk about that adjusts each feature very proportionally. So this technique is especially useful when you want all features to have in the same scale, okay, and but still preserve the relationship between the values. So you are worried about the relationship between the data sets, but you want them to be on the same scale. On the on the other hand, when you talk about the Z-score normalization, which is also been famously called as standardization. So basically what standardization does, standardization transforms the data so that it has mean of 0 and standardized deviation as of 1. So basically unlike the first method, which is the min max scaling, standardization does not bound values to a fixed interval, but instead they express them in terms of the standard deviation from the mean. That's the difference. So this is useful for algorithm that assumes the Gaussian distribution, like some way normal distribution. Basically when you have some kind of statistical random data, they are sensitive to differences in in feature variances. So the main takeaway, choosing between this min max scaling and the standardization method, that depends on the algorithm you are using and the data distribution you are using. So min max scaling is better when the data is already has a bound region, or you kind of bound the range, whereas standardization is better when the data has outliers, some kind of noise is there, some kind of outliers are there, that means they have some kind of varied distribution. That's the period when we try to use the Z-score normalization or standardization. And then if you try to look into how to choose the right normalization technique, not all data sets are same, as we know. So it's important to align the normalization method with the data type also and the requirement of your machine learning algorithm, right? So the min max scaling, if you will look into that, this is the best when your algorithm expects input features to be very specific range, such as neural network or SVM. So those are the best places where we kind of use the min max scaling. Always handle the outliers beforehand because they cannot distort the scaling, okay. Whereas if you think about the Z-score normalization or the standardization, this works very well with the algorithm like clustering, like k-means clustering or linear regression or logistic regression. So those are the places they assume normally distributed data and it centers the data around 0 and a standard deviation of 1. That makes it very easier for these models to converge. So that's the place where most of the clustering cases we kind of try to use the standardization. And then for sparse data sets where most data values are 0, right? That's the period when you use function, or we use the method called max subscalar. These are actually designed work well without distorting the 0 entities, okay. And then another important factor is that categorical data. So what if we will be having categorical data. So for categorical features, what we do, you will often need to apply techniques like one-hot coding, right, before normalizing the data, so that scaling remains meaningful and that does not introduce any kind of outliers, that does not include any kind of bias. So the choice of normalization technique, there are also varieties of other normalization techniques which I have not highlighted. These are the main important ones, especially when we talk about the infrastructure monitoring. These are the main important ones which we use. The choice of the normalization technique, that depends on the specific characterizations of the data or how your data is, whether do you have already introduced some kind of outliers, or you need to kind of use what kind of machine learning model. That's also some way is important when you are selecting the types of normalization and your model. So experimentation and evaluation of the impact on the model performance are a very key way to apply the normalization effectively. Then another important part is the feature scaling. So another key step is the data processing in the feature scaling. So the feature scaling is basically nothing but standardizes the range of the independent variables or features in a data set where no single feature dominates during the model training or the analysis method. So why feature scaling is important? The main importance of this kind of feature scaling, or the main goal of this feature scaling, is to bring all features to a similar scale of range, right? And that will prevent, or this prevents features with large magnitude from overshadowing the others. And that will help the convergence study, that will help the convergence period of the optimization algorithm, that will also kind of help to reduce the numerical instability before the training, okay, or the during the training. And if you see this kind of methods, you can see that the scaling features ensure that the machine learning algorithm treats all features very equally. This prevents all biases towards the features with larger scales and enhances that the convergence of all algorithms like gradient descent, speeds up the training. It also makes it very easier to interpret the data as well. So in addition, if you will see that the previous to normalization method, which is the mean max scaling and the Z-score normalization, they are also other useful technique to do the feature scaling. Okay. And this is also use a method like max-up scaler. This is also use the robust scaler. So the robust scaler is basically a statistics or a method. They are being used when there are some robust outliers, right? Such as median or some kind of IQR range to scale the feature. So it's actually ideal where the outliers are distributions. Okay. So in summary, you can quickly, if you will try to look into this feature scaling, you can see that they not only help the model to converge easily or converge quite faster, but they also ensure that there are no bias, right? They ensure the fairness between the features so that any large data set will not dominate the small ones. And choosing the right scaling method is also very, very important because that will also depend on the data characteristics and model, that means the machine learning model you are using to analyze your large scale data. So then when you think about the practical guidelines of applying this feature scaling, since not all datasets and model behave the same way, we know, right? It is important to pick the scaling method that is best matched with the data and that will best match with the algorithm you are going to use. So as I said that the standardization is very, very important, right? Because using this, your data follows a very normal distribution, or when you use the algorithm like linear regression, logistics, so they or k-mean clustering, that standardization actually very, very important because they centers the data around 0 with a unit variance and then they make it ideal for all of this model to analyze the particular case. And as I said, the normalization like mean max scaling, that's also very, very important because when you use this one, using this you need your data with a specific range like sum is 0 to 1, such as neural network, support vector. Those are the places where we do use it basically, and it is useful when we preserve the relative size of the featuring is important, right? And then as I said that again using the same one, the main feature scaling is not one size fits all. So machining is or matching is the right technique to your data types or the algorithm to ensure the faster convergence, to make the computationally efficient, to improve the model performance and more stable results. And then the next one is coming around handling the categorical data, so which is another crucial aspects of the data preprocessing. So when we talk about the categorical variables that represent the groups, right, or categories that are often non-numeric or which poses the unique challenges of the machine learning model. And the key challenges and the considerations what we see is one is the non-numeric representation. So basically categorical variables are typically stored as strings or the kind of stores as a level. That means which is most machine learning algorithm cannot directly take, okay, or cannot directly process to analyze. So we need to convert them into the numeric form so models can use them to train and predict, okay. And then there is another challenge is that ordinal and the nominal variables. So the categorical variable can be ordinal, that means with a meaningful order like low, medium, higher, or they can be nominal. Nominal means that they can inherit like red, blue, green, right? So it is very, very important to introduce some kind of biasness in your model prediction. So that's the another important issue with this kind of class of dimension. So basically when you try to approach this categorical data, that's the another issue we kind of look into. So in summary, you can see that handling this categorical data carefully is very, very important because by converting it into a suitable numerical form or respecting its ordinal and nominal nature and managing its dimensionality, it is very, very essential for creating the robust and efficient machine learning model, especially when we are talking about the different kind of data sets which are being actually available in your data, right? So then another important or the main techniques for encoding the categorical variables are level encoding. Since most of the machine learning models, they cannot work directly with the text-based categories, right? We need to convert this into the numerical value, especially when we talk about the machine learning. And level encoding, they assign, so level encoding is one of the types what we use it. So level encoding is a method or they assign a unique numerical level to each of the category into the categorical values. Like for example, if you think about dog or cat, they might be encoded as 0, right? And the dog can be encoded as 1. Or maybe if you have rabbit, they can be encoded as 2. So that's how generally machine learning model understands, right? However, for nominal variables, you can see without order, label encoding may unintentionally include some kind of false hierarchy. So then another example is that if you have some kind of label encoder to demonstrate how the label encoding works in Python, MATLAB, whatever you use, we generally what we try to do is that we import the label encoder, create an instance, and then fit and transform a list of categories to the numerical level. So that's what the machine learning model understands, right? And this process then converts text data into the numerical data. From that, machine learning model can further analyze it, right? Basically, in short, you can see that label encoding does work. Label encoding is simple and efficient for ordinal categories, but you need to be very, very careful about using it on purely nominal data to avoid introducing any kind of unintended bias. Basically, what we try to do is that we try to make our data more user friendly so that the machine learning model can further analyze it, right? That's the main target of this one. And then the another important, the second common technique for encoding the categorical variable is, as I said, one-hot coding. So while labeling, the encoding assigns a single number to each of the categories. So what one-hot coding takes a different approach. So what they do is that, so one-hot coding actually creates the separate binary columns for each category in a very categorical variable. So each of these new column, they indicate whether they particularly categorically present in 1 or absent in 0 in a row. So that's how generally it works. However, you have to keep in mind that one-hot coding can increase the dimensionality. That means it can make your calculation very, very complex. It can make your data set quite big if there are many unique categories. So if you have too many categories, this can make your data much more dimensionally big, right? And that can affect the model performance. So in that way, you have to use some kind of machine learning model which can actually handle the large dimensional cases, right? So then there are, in summary, you can say that the one-hot coding is go-to approach for nominal data because it preserves the categoric distinction without introducing any kind of bias by numerical or from numerical coding. But you have to keep in mind that when you use that, what kind of machine learning algorithm you are attaching to, so that it will be capable of taking the large set of data or large dimension of data. Like we cannot use it most of the feeding cases, right? So you have to be very, very careful when you are selecting that kind of machine learning module. And then there is another third technique to encode the categorical variables is the dummy encoding. So it is very, very similar to the previous one, which is the hot encoding, but with one of the important difference. So dummy encoding that creates the binary column for the category like one-hot coding similarly, but it drops one of the columns, right? So this prevents multicollinearity, a common issue which happens in the regression models. Okay, so where the one column can be predicted from the other. So by dropping one of this category, what happens? The remaining column uses it as a reference category. So the encoded data more suitable for model like regression model or the logistic regression or any kind of other statistical model. We do use the dummy encoding quite a lot. It's very, very similar to the one-hot coding, but there is only one difference that we kind of drops one of the column in that case. And if you take the summary of this kind of or understanding of this dummy encoding, you can see that it's particularly helpful for the regression model, as I said, where the interpretability and avoiding the multicollinearity are critical. So that's the place where we kind of try to do that. It's very much kind of statistically sound version of one-hot coding for this kind of cases. So then if you will try to understand the discussion of the categorical data by focusing on best practice and guidelines of handling it correctly, you can see that there are, they are getting into the right part of it, or the right can prevent major issues downstream in your model. So the first one is understand the variable types. That's very, very important. That first always identify whether your categorical variables are ordinal or nominal, right? This determines that which encoding technique you need to use or which encoding technique is more appropriate. For example, label encoding works better for the ordinal, right? Whereas the one-hot or the dummy one is better for the nominal cases. Then also you have to be very, very careful about the ordinal misinterpretation. You have to be very careful when applying the label encoding to nominal variables because since it assigns a number of categories, it can also introduce some kind of false sense or some kind of hierarchy when nothing exists as well. And dealing with the high cardiology. So that's also very, very important because those with the large numbers of unique categories can make the encoding very tricky, can make the encoding little bit dimensionally more. So in these cases, you consider techniques like frequency encoding, you consider like target encoding, even dimensional reduction methods can also be used. So you have to understand what variables you are having, what categorical variables you are having, and according to that, you actually try to use the categorical data and try to use the method. So basically these guidelines go hand in hand with everything we have covered in the previous slides, from handling to missing values to normalizing the numeric data, right? Together they kind of ensure that your data set is clean, your data set is efficient and ready for high performance machine learning model. Now the another important part of the common challenges are that dealing with the imbalanced data, right? So imbalanced data can lead to biased models and that favor the majority class and perform poorly for the minority classes, and this can actually bias affect both model training as well as evaluation. So model trained or imbalanced data tend to prioritize accuracy on the majority class. So basically the importance of this is that if you try to think about this imbalanced data or the importance of this, you can see that this is very, very important and that can lead to biased model if you do not consider it properly. And then again another important practical technique for dealing with imbalanced data is that techniques for handling the imbalanced data. So after understanding the impact of the imbalance from the previous slide, we now need to understand the strategies how we can fix it up. So one is the oversampling. That's another method we do quite well. And how we do that? This basically involves increasing the number of instances in the minority class, either by duplicating existing samples or generating synthetic data. And that will help to balance the dataset without losing any majority class information. Okay. And another way what we can do is that is the undersampling. So basically we reduce the number of instances in the majority class and to match the minority class, right? And this can be effective by many lead to the loss of the potential valuable data. Another way is the hybrid approach we can do. So you can also combine oversampling and we can combine undersampling to strike a balance between preserving the information but also reducing the class imbalance. So that's the mixing of this we can do. There's another important one is also class weighting. So they are actually being used where you assign a very higher weight to the minority class during the model training. So there are several techniques and ways we kind of do that, but the main techniques or all the techniques actually help us to improve the model fairness, help us to improve the model performance, especially for critical application like fraud detection, medical diagnosis, anomaly detection in a very early stage, when minority class are often used for most importantly identify the particular cases. So now if you will try to look into the impact of the imbalanced data and the methods to address it, so you can see that there are key points that how to do that. First is that understand the data distribution, that what distribution the data is following, the class of distribution in your data set and how severe the imbalance is. That's very, very important for us to understand because that will help us to decide the technique is more suitable or not, right? Another is that choose the appropriate technique. Select either oversampling, undersampling, hybrid approach, whatever factors works best, right? And then evaluate the matrices. So accuracy alone can be misleading with imbalanced data. So you have to use more informative matrices like precision. Those are the things you need to do that. And then the cross validate. So to convert your study. So apply these techniques with the cross validation polls to avoid that any data leakage or ensure that your performance is actually kind of estimating the reliable or realistic data. So there are a lot of other guidelines also, but these are the main important ones to highlight that this guideline will help us that our model fits all class very fairly. There will be no biases towards any majority class and they deliver more trustworthy and the balanced performances. Okay. So now if you will try to look into the the real life example, let's try to take the real life example. There are numerous in situ structures and laboratory test structures have been designed, especially when we think about the structural health monitoring. And these case studies are used to illustrate different concepts throughout the world, right? So what are the methods which we try to do that? The first one is that recurring the structures and consistency, right? So because the structures appear repeatedly, we try to summarize the descriptions and then we try to understand that. So I will say that you kind of try to look into this particular problem and think about whatever we have discussed today, how we can actually, by using the data processing, sampling, and how we can actually take care of this particular case when we talk about the example of the SHM cases, right? And you will see that once you will understand whatever we have discussed today to the any kind of SHM problems you take, this approach actually will give you very transparency, consistency and traceability of the SHM data handling, which is very, very critical when we talk about the elements of the reliable research approach, right? So now let's try to quickly see one or two questions so that because we understand it's quite theoretically heavy today, but let's see where we kind of stand. So what does an accelerometer measures? Does it measure temperature, vibration, humidity, or acoustic? Vibration? So B is the correct answer. So give one example of an industry application of the accelerometer. Any kind of, think about more civil infrastructure application. So what can be the example?
Machine foundations on vehicle acceleration.
Sorry?
Machine foundations on vehicle acceleration and bridges.
Yeah. Anything else? Do you think about more civil structures and all? Detecting the ground movement, right? If you think about the earthquake. What else? How we can use the accelerometer?
Detecting the axle.
Sorry?
Detecting axle of vehicle passing through the road.
Yeah. I cannot hear you, sorry. Yeah. And if you kind of convert it to more the strain gauges compared to the accelerometers, what is the very important industry application? Yeah. What else?
Modulus of electricity and Poisson ratio, we can use calculating that.
How we can do that using the strain gauges?
If we can fix the strain gauge to raw sample and we test in a compressive testing machine,
Yeah.
then we can use.
Yeah. Any other industry application? Think about all the sensors we have talked today. Temperature, humidity is very straightforward. This is a very all kind of environmental factors always will be an issue. But you will see that the accelerometer, strain gauge, even the AE sensor, that can actually be used a quite lot of varieties. Especially the example we have given, which is not quite industry, but we need to use tensile testing case, compressive case, fabric case. So we do use quite those kind of sensors. Also try to think about that. What is the broad application of this kind of sensors, right? So then when we talk about the strain gauge, how does it measure the changes? Does it actually measure the electric resistance, right? Okay. So now if you will kind of try to summarize what we have seen today, but we have seen the machine learning algorithms. We have covered the supervised, unsupervised, reinforced learning one in the beginning, right? And then the second one is like quite intensive, where we try to see the data connections and the sensors which are important for the infrastructure monitoring, the accelerometer, strain gauge, the fiber optic sensors, how those are important, and then the data processing method, right? So we just emphasize important. That means we are interested about data cleaning. We are seeing the scaling method, the normalization, handling the missing data. We have also kind of tried to little bit cover the encoding categorical technique. But as I said, this is a very kind of machine learning based method. So we could not cover a lot of this, especially when we talk about the encoding method. So I will say that I will also share some of the references. If you are interested, you can go into details of that, and I will be happy to share some of my papers or some of the resources if you need any further information. And then we have also seen the big data today, the understanding the importance of the big data, how we can handle the large data sets, right? And highlight the examples of the successful data quality. So those are the important ones. Definitely we have looked into a lot of data processing techniques today. So the main key takeaways, you will see that how effectively we can collect the data, process the data, and understand and connect it with a reliable machine learning approach. That means choosing the right algorithm, choosing the right sensor. So we have seen the advantages of sensor, limitations of sensor. So how we can actually choose the correct one, and handling techniques which will improve the model performances or the structural reliability. So now if you will go through the all slides, so I will say that also try to think about the advanced machine learning topics like how the deep learning can actually architect. So we have not talked about CNN, we didn't talk about RNNs. So I will say that go and have a look into those, because those are also very, very important when we talk about the infrastructure monitoring, and think about for the time series case or for the image based case, SLM data, how this can be processed further. We also try to investigate the transfer learning and few short learning, because those are also small level data sets when we talk about the SHM cases or for the infrastructure monitoring. They are very, very important. And then another important factor, I think, you must if you are kind of looking into the literature or something very, very kind of nowadays going on in explainable AI. So you will see most of the projects and paper, this term is being used quite a lot. So do you know what do we mean by explainable AI? Have you ever heard about this term explainable AI? Okay, then go and try to read what we mean by explainable AI. Okay, they are actually being used to interpret the ML models for the engineers so that we can understand the decision making very seriously. But they are actually some way, you can say, some kind of fancy terms, but it is actually targeting some specific effects, especially when we talk about SSA. So deep learning architecture, transfer learning, and explainable AI, and how they are actually helping. So they all are modern advanced machine learning models which are recently being used in SHM, and I will suggest to have a go and look into that. Try to look into more about image processing data or time series and how it could possibly be applied there. And again, as I said that, so these are the references that we have used throughout the slides, and these are the references. So I will share these details once the lecture will be over. So you can take a photo, or anyway I will share the details with this also with you all, with the with the sense of the details. So all the further studies of the whatever we have talked today or covered today, everything is from there, from the sources which I have given, and then there are some extra resources also which will be helpful for you. So if you don't have any further questions, we will take some further questions, but we will end the lecture here. And again, we will see tomorrow to kind of see the pre-processing and feature extraction. But before that, let's try to see if there is any online questions. Yeah, so Abhishek, can you see if there is any online questions? Sorry? Yeah, some way I'm not able to. Yeah, so it's not opening. That's why it's just mirror based. That's why I was trying to get into that. Let me just open the meter. When was no, I think no, it's okay. I think I can leave it. Yeah. Now it is. And this is all on. Yeah, so I think he's asking about applications of sensor inside the structure or the outside the structure, which will give more accurate results. Okay, yeah. So it depends on the sensor you are actually using on that whatever sensors you are going to use it. Depending on that, you actually kind of need to understand how to install that and where to install that. And then each type of sensor can be used to fix inside the concrete cube. So there are nowadays some modern types of sensor which is actually being used, and they are kind of being molded with some kind of metals, and then they are being introduced inside the concrete cube. So that's definitely another lab-based sensor also. So there are a lot of new techniques that people are using inside the sensor inside the concrete cube to monitor that. Except that definitely you can actually attach that on on the side of concrete cube and monitor that. That's one of the very very conventional way we can do that. So simple way to reduce the size of the data. Yeah, I think I have mentioned few of the techniques today. So any of the techniques you can use depending on the limitations you are kind of taking care of. You can actually take care of the reducing the data. And then he's asking about acceleration, strain, yeah, so I think I have talked about the different kind of sensors today. If you will look into that, so those are the main type of sensors, the temperature, acoustic, humidity, and when you look into that, so all of the sensors also have some different applications, and I have talked about those. I will say that have a look into that. Those are the main applications with the direct application we generally use, rather than only calculating or evaluating the failure or the damage. Yeah, I think he's asking the same one. So Anand, do you have any further questions? Because I think I can see the same questions. Yeah, I think it's okay. Yeah, I said lines. Yeah. This is the same one. It's the same one. Okay. Yeah. So anyone of you has any further questions today? Yes.
Couple of things.
Okay, so I think we will end the lecture here and then we will take the questions after that, right? Because I think we are already running with the time, right? So thank you everyone who actually joined online, and we will end the lecture, and if you have any further doubts you can always reach out. Just disconnecting it. Yes, now you can say. Yeah.
That was actually vast amount of data.
Yeah, can you just come back? I can't.
It was a huge amount of data which
Yeah.
was presented. We were not.
Yeah. So I will share the the details of this one, because there were a lot of details. But if you will look into that, most of those were very theoretical compared to the previous one, and then there was not many things to kind of understand rather than to learn. So I will definitely share the resources and all, where you can kind of see the variations, and I can also share the slides from you, right? Or resources of that. Yeah, from the video will be shared with you all. So then you can actually refer those. But if needed, I think also I can share the resources with you all. So you can refer those. But most of the cases you will see that's very theoretical. So
Because all the presentations were very different. This was
yeah. Because there is like lot of there will be always some theories you need to know that, and then you need to apply to the next one. So today's was like very theoretical compared to the previous one. But it is very important to know all of this normalization and cleaning and all of that. But we cannot also get into very details into that, because we have other lot of things to cover. But we cannot cover those unless you know what is data cleaning is, what is normalization is. You need to know about the biases. You need to at least be aware of this particular terms before we get into the next one. But don't worry, we share all the details. You don't need to be worried if there is too much information there.
So three generic questions from the lecture. We have different types of infrastructure, like you have masonry, you have steel, and you have concrete.
Yeah.
You said there are three types of steel layers, like quarter, half, and full.
Yeah.
So where exactly we can use? Are these three used for the same concrete, or are these different for different
So
infrastructure?
as I said that the limitation and advantage, when you need very precise one, you use the 4-1, right? When you need a very fast and very like user friendly or very cost efficient, then you use the first. So that does not depend on the type of it depends on the limitations and the advantages I have mentioned. It does not depend on the type of material, but it also depends on some with the temperature perspective. So the 4-1 is very good, and we have a wide range of that. But it does not depend on steel, concrete, or composite. It depends on the limitations and the advantages I have mentioned today.
Because we were also saying about the sensitivity of measuring this thing, because
Yeah,
it is
sensitivity.
very different in three different
Yeah, so that is actually depends on what sensitivity you are interested about, right? So that depending on that you will select the strain limit. It does not depend on what materials you are interested about. It depends on what sensitivity you are interested, how precisely you want to do that, and how fast you want to do that. So those factors will be kind of reason to select your strain rather than what material you are attacking to that, where you are attacking to that. Those are installation methods. Those are like extra add-ons, but that's not going to affect you to select the strain gauge you are interested to install.
Same question was asked in online. When we use data compression for images or like weather data, like you have given about Snappy or JJ. So what is the amount of compression happens? Like 10%, 20%,
Yeah.
30%?
That also depends on the way you want to do it. How much? It's like you have seen, right? That when you try to compress you have a lot of files, right? You want to send it over the email. So what we do is that we kind of we don't want to compromise the quality of the data, right? So we have to remember we don't want to compromise the quality.